So in finding these volumes, we're going to start by calculating the area of what happens to one slice. And so let me zoom in right here. You're going to take that slice. Now, it's important that that slice has to be perpendicular to your axis for rotation. Someplace I think I mentioned that. I'm not sure. It was probably pretty subtle. I don't want you to miss it or anything like that. But your slice has to be perpendicular to the axis of rotation. If it is, great. If it's not, then you're not going to be doing the shell or washer method, the disc or washer method that we're going to be doing in this section. When you take that slice and you rotate it around an axis, it kind of traces out a disc. And that disc shape is going to be right here for that one shape. We'll approximate the volume of this solid by adding up a bunch of little discs. Now, when we add up that bunch of little discs, that's going to be an approximate area. If you wanted to find that area exactly, what do you think I'm going to have to do with this approximation to make it the exact area, or exact volume as opposed to an approximate? Yeah, you're going to have to take a limit. Now, the expressions involved get a little bit ugly, but you are eventually going to be taking a limit. It looks something like this. We're going to keep it a little bit more simple. We're going to focus on the volume of a solid. In our particular case, we're going to start by finding the volume of one slice. As it rotates around the x-axis, it's going to trace out a disk. And we're going to add up the area of all such disks. So let's start with example A here. And since we're rotating around the x-axis like this, I'm going to take a slice perpendicular to that. Does that mean my slice is going to hit the x-axis or y-axis? All right, this wasn't supposed to be a trick question. X-axis or y-axis? dx slice or dy slice? dx slice. Perpendicular to your axis of rotation. So let's squeeze that in here. There's my one slice. When I rotate that around an axis, I'm going to get a disk. And I want to find the volume of that one disk. So let's start with that. Volume of one disk. Well, the volume of that one disk, now that disk actually looks like a really short cylinder like this. And in as much as we're still in the hockey playoffs, Stanley Cup Finals, you can call that the volume of one hockey puck. I want to find the volume of that puck. All right, this is disappointing. Some of you don't know that the Stanley Cups are still going on, but that's okay. All right. Now, how do you find the volume of a cylinder? Well, it's going to be the area of this times what? The height. So it's going to be the area. Now the top of this is going to be the shape of a circle. So it's going to be pi r squared times this distance. What's that distance? dx. That's your distance over here. So that's dx. Think back for a moment in terms of section 6.1. When we ended up with a dx term here, what did that say about the rest of my expression here? It has to be in terms of x. So I need to know what the radius is. So what's the radius here? R. The radius is going to be the top minus the bottom. Well, that's not too bad. R is top minus bottom. So in our particular case, what's the top function? Does anyone know? X plus 1. So R is x plus 1 minus 0, or just x plus 1. I can take that and put it into my volume formula and end up with volume equals pi times x plus 1 squared times dx. And that's great. That's exactly the volume of one disk. Okay so far? All right. But I need to add up the volume of all such disks. So what do I have to do to add up the volume of all such disks? Well, technically I'll be taking the limit and that'll turn into an integral. But let's just jump to the happy ending. I need to integrate. I'm going to take the pi out here and write x plus 1 squared dx. But there's one last little thing that I need here.
I have a question about radius. If that's supposed to be the radius, is that half?
Because you're rotating, no, it is half. Because remember, this is going to rotate all the way around underneath the x-axis. So, yeah, that's the radius.
Gotcha.
Is there another question, Amavalaji? No? Good? All right. There's one last thing that I need. My limits of integration. Nick, what do we got for the limits of integration?
2 and 0.
Yeah. So the farthest to the left that this slice can be taken is at 0, and the farthest to the right that it can be taken and still be in that little area is 2. So 0 to 2. Great. Now, I'm not sure I want to take the time with a polynomial like this to do this out by hand. I trust that you can integrate a polynomial. Let me show you the trick that you're going to need, though, to give me the exact answer I'm going to look for. Let's clear this out. If I type in my integration like this, pi times math 9, integral from 0 to 1 of x plus 1 squared. Now you got to come inside the parentheses and put x plus 1. You'll need 2 sets of parentheses. X plus 1 squared, and then a dx. It's going to give me a nice numerical answer, but when I hit my favorite key, the math key, answer to fraction, it's just going to give me the same numerical answer. I'm like, well, that's not helpful. My instructor wants an exact answer. So what you could do is repeat your calculation, except get rid of the pi. Yeah, question?
You put 0 to 1.
0 to 1? Oh, it should be 0 to 2. My bad. All right. But the point will still be the same. Your calculator is not going to be really good at doing the answer to fraction trick if you don't have a nice, neat fraction. Here, when I got rid of the pi, now it knows that, okay, that fraction is really 26 over 3, and then just put in the pi afterwards. So the final answer is going to be 26 pi over 3. Now it's for your functions that have nice polynomials that I'll let you get away with the fn int, and I'll specifically say on your exams, you can use fn int to finish the problem. I do need to see the setup though. How are we looking on example A? Pretty good there? Thank you. Any concerns? Something that maybe I went over a little too fast? Lillian, doing all right? Okay. Let's try again with example B. Again, we're going to be rotating around the x-axis. So let's take a little slice in terms of the x-axis. So let's make our slice here. So that's going to be a dx slice. And let's set about trying to find the volume of the disk that we're going to get. Now it's a disk because this area is flush with our axis of rotation. If there was a gap, well, then that's going to be a little bit different. So for right now, we're going to work on finding the volume of one disk. And maybe I'll draw another little hockey puck over here, just for giggles. So there's our little hockey puck, our disc. We're trying to find the volume of that one disc. Now that disc has a radius, which is r. The volume of that one disc is simply going to be pi r squared h, which is the volume of a cylinder, pi r squared h. But the big chore for us is going to be to figure out, well, what's the radius in this particular case? So let's figure out the radius. Well, that's again going to be top minus bottom. Which in this particular case, the top function is the square root of x minus 1. The bottom function is 0. So it's just the square root of x minus 1. That's your radius. There's something rather convenient about that. When I plug that into this formula over here, when I plug the radius into here, what nice thing is going to happen?
The square root is going to cancel.
Yeah, square root's going to cancel. So I'll just get pi times x minus 1 dx. And the integral that I'm going to need is the integral, well, let's see. I'll take the pi out here, x minus 1 dx. What limits of integration should I use here? Ah, nice. You got to look at your region here. The region starts at 1, goes up to 4. So those are going to be my limits of integration. 1 to 4. Kind of want to do this one out by hand, just because I don't want to do everything on the graphing calculator. So it's going to be pi times 1 to 4. Actually, I need an antiderivative for this here.
X squared over 2 minus x.
Good, x squared over 2 minus x. So let's see. It's going to be pi times the upper limit. So 4 squared over 2 is going to be 8 minus 4 would be 4 minus 1/2 minus 1 is going to be negative 1/2. And when I put that all together, I'm going to end up with 9 pi over 2 for my final answer. Sorry I ran out of a little room there towards the end, but you should be able to find the antiderivative of a polynomial. That is something that I kind of expect, but I'm not going to ask you to do it very often. Mostly it's going to be other functions. How are we looking on example B? Rolling through the stuff, easy A for the next exam. No? All right. Well, let's do a little more practice. Start getting you involved a little bit more.
These are still rough approximations, right? They're not fixed limits.
No, these are exact answers. So the stuff about taking the limit is a step that I've kind of bypassed just for sake of simplicity and presentation. So technically right here, you could, once you find the volume of one disk, you can set up a Riemann sum like this and add up the areas, etc., and then take this limit. But that limit's going to be pi times the radius squared in the interval of a to b. So I just kind of jump to that right away. I don't really pass through the part where I'm doing the limits. So no, these are exact answers. They're no longer approximations. Thanks for the clarification there. All right. You ready for one? So I see a couple people swallowing hard going, Okay, all right, steel yourselves. Try this one. Again, we're gonna take a DX slice in this particular one. DX, start by finding the volume of one disk. But it's a horrible looking disc, but oh well. So it's only polynomials that I'm gonna let you get away with using numerical integration. This one's not gonna have a polynomial. You're gonna have to do this one with exact arithmetic or exact algebraic expressions. So you can check yourself when you're done with the graphic calculator. I'm guessing you're probably gonna need a U substitution. Unless you're pretty good with the antiderivatives.
Square that, that's fine, but so when you move the parentheses, you get two x, not x squared. And you can't integrate it like that. That's just a two x.
Yeah. If you take the derivative of this, you would get 4 e to the x, e to the 2x. So it would be the opposite, the reciprocal.
Charging the U substitution. Okay, so far so
We're using U substitution.
you said
And here we have another x, right?
it's okay, you don't need another, made a little mistake here. We have e to the x squared, you move parentheses, it's 2x, not x squared.
So it's actually,
So the x one should have 2.
Do I just leave it like
Only if you want full credit.
that? Okay. Cool.
I think that's good. within myself that way. Good job. Let's get rid of the parentheses, and when you do that, you get 2 times that.
Can I combine these or do I?
No, there's
Okay.
There's not much you can do there. Yeah, just kind
I
of
was
stuck
looking
on that.
like, can I combine those still? And I was like,
No, it looks tempting. I mean, there is something kind of strange you could do with it, but no, not much you can.
Unless you were to factor out like an ease.
No, I think it's like the hyperbolic sine of -4, or hyperbolic sine of 4, I think it would be, yeah.
I'm just gonna leave it as is.
Yeah, probably not a bad idea. Okay, so let's look at this one. I want to find the volume of one disk. Here's my R. The height here is going to be another dx. So that's this piece right there. R is going to be top minus bottom. In this case, it's e to the y, or e to the x minus 0, or just e to the x. The big thing that we need to clean up for a few of you is this. When I've got e to the x squared, let me do it this way. That's pi. When you square something, you're multiplying it by itself. So I get e to the x times e to the x. What happens with their exponents when you multiply things with the same base? You add them. X plus x is 2x. Or up here, you can say, oh, these multiply. Either way, you should end up with pi times e to the 2x dx. A lot of people had an x squared. If you had an x squared, you're really going to have a tough time trying to integrate this one. As far as the integral is concerned, let's do that up here. So it's going to be the integral from -2 to 2. I'm going to pull out the pi, e to the 2x dx. Well, some of you might get good at this, and that's great. You can see the antiderivative. If you can't, then we're going to need to do a little u substitution. Let u equals 2x. du by dx would equal 2. So du would be 2 dx, or 1/2 du equals dx. So now I can make my substitution, but I'm probably also going to want to change my limits of integration. So let's do that as well. So I want to know what happens when x equals 2 and -2. That one's 2 and -2. So u of 2 would be 2 times 2, which is 4. And this would be -4. The nice benefit about changing your limits of integration is that you don't have to look back in terms of x. We're done with x. It's gone. This is going to be the integral from -4 to 4 of e to the u times 1/2 du. That 1/2 can come out in front along with the pi. I need the antiderivative of e to the u. Just e to the u. So we'll write it this way. Pi times the function evaluated between -4 and 4. That function is e to the u. It's going to be pi over 2. I think I said pi. It should be pi over 2 times e to the 4 minus e to the -4. And that's it. That's a nice exact answer. So exact answers are going to involve pi and e and square roots and stuff like that. You can check it with your graphing calculator and see if you can't come up with the same decimal answer, but that's not what I'm going to be looking for on an exam. Are we okay with example C there? Let's try example D. Example D, you can do a couple different ways, but I think they're asking for one in particular. In fact, I take that back. You don't have much choice in example D. What's different about example D than our previous examples? Yeah, you're rotating around the y-axis. But this is actually, and you can quote me, and I'll quote it back to you when I hand back your exams. This is actually a problem on your exam, whereas you need to figure out what kind of a slice you're going to take. In this particular case, because you're taking and rotating this around the y-axis, rotating it this way, you have to take a dy slice. You have no choice. You have to take a slice of something perpendicular to the axis of rotation. So let's squeeze that in here. There's our dy slice. That's our dy slice. Because this figure is completely flush with your axis of rotation, you're going to get a disk when you sweep that around the y-axis. So let's see if we can't find the volume of that one disk, or as I like to think of it, as a hockey puck. So the thickness of this is now going to be dy. Okay, great. Let's see about finding the volume of one disk. Volume of one disk. Well, it's still a cylinder, a very short cylinder, so it's still going to be pi r squared times the height. But the height in this case is no longer dx, it's a dy. And that dy is telling me something about my problem. Ashley, what's that saying for the rest of my problem here? Perfect. Has to be in terms of y. So my radius is going to be the distance between this axis here and my function here. So that's going to be r. And r is going to be the rightmost function minus the leftmost function. So r, the radius, is the right minus the left, which is going to be 2 square roots of 7y minus 0. Or just 2 square roots of 7y. Okay, let's plug that into our formula here. See if we can't find the volume of one disk. So volume is going to be pi times 2 square roots of 7y squared times dy. I would always recommend simplifying this expression before you put it into your integrand. Let's simplify it here. Nate, when I square this out, what will I get here in the parentheses?
4 times 7y.
4 times 7y, and 4 times 7 will be 28. So let's just put that right there. Great. Now it's just a matter of integration. I'll take the pi out in front. Pi times the integral of 28y. Actually, I probably should have taken out the 28 as well. What should I use for my limits of integration though?
0 to 3.
0 to 3, good. They gave you up at the top here, they gave you that one of the bounding functions is y equals 3. So that's going to be our upper limit is 3. The lower limit comes from the fact that the smallest value of y for which you can still be in this region is 0. You can take the dy slice all the way down to 0. So 0 to 3. If I take the 28 out front, that's going to be pi over, 28 times a function y squared over 2 between 0 and 3. If I plug in the 3, I'll end up with 9 over 2 minus a 0, which is going to give me a 0. So 9 over 2 times 28 over pi. The 2 is going to cancel. So I'll be left with 14 times 9, which is what, 126? So 126 pi when it's all said and done. Whew. So the tough part is going to be setting up the integrand. And as I grade your papers, you know, lots of little partial credits. I want to see the right limits of integration. I want to see that you've taken the proper slice here. Should it be a dx slice or a dy slice? I want to see the right integrand, and I want to see the right final answer. But there's a lot of opportunity to get lots of little pieces of partial credit. Okay. Any other thoughts on example D here? I know that might not be in your comfort zone as much, but do be ready for something that goes around, say, the y-axis, or there's another little twist of fate that we can give you, and that's an example E. And again, this is going to be another one around the y-axis, except this one's going to be a little bit more involved. We'll rotate around the y-axis. Tony, what kind of a slice am I going to have to take if I'm slicing around the y-axis, or rotating around the y-axis? Yeah, horizontal. So it's going to be a dy slice here. Thank you so much. But can anyone notice something different about what's going to happen here as opposed to what happened in the last one? As this rotates around the y-axis, what kind of a figure is that going to trace out for me? Well, let me go back to the top of the handout, and I'm going to go back to it over here, because I think it'll show up a little bit better. Let's go all the way back to this part right here. And let me copy that and kind of try and blow it up a little bit. The difference between this one and the last one is that my figure doesn't exactly quite touch the x-axis or the y-axis, its axis of rotation for the whole length. So when I rotate this around the axis, I'm really going to be leaving a hole here. So instead of a disc, I'm going to have kind of a washer shape when I rotate it around the y-axis. So instead of finding the volume of one disc, I'm going to have to try and find the volume of one washer. So volume of one washer. And so let's try and draw a washer, at least roughly. All right, so this is very rough, but it'll work. Now, to find the volume of this thing, what I could really do is try and find the volume of the outside part, the volume of the outside cylinder, and subtract off the piece that's missing, the volume of the inside cylinder. Now, if you want to wait till the happy ending, that's fine. There's going to be two radius. There's going to be your R1, which will be in here, the radius to the innermost part, and then R2, which is going to be the radius towards your outer part. And really what we're going to do is we're going to try and find the volume of each of these and subtract them. Now I don't think it's really worth your time to copy it down, but it's up to you. So the volume is going to equal pi r squared 2 times the thickness, which is dy, minus pi r squared 1 of dy again. So it's just the outer cylinder minus the inner cylinder, leaving you whatever's left. But I'd probably clean that up a lot. I would clean that up by factoring out the pi out the front and the dy out the back. So it's just pi times r2 squared minus r1 squared dy. And that's the thing that we're going to need to concentrate on filling in. So it's very similar to our work with the previous one. It's just we've got this little gap in between that we've got to take account of. So I got to figure out these two things. I got to figure out expressions for R2 and R1. Let's keep track of which is which. This little piece right here, and then I'm going to have another piece out here. That's my inner piece, that's going to be the R1. This is my outer piece, that's going to be the R2. Kind of like before, it's going to be right minus left. So the rightmost function, in this case, comes from this part. Y equals x squared. But I know I need to have this in terms of y. So what should I put in here for an expression that involves y if all I've got is y equals x squared? You kind of need to solve for x. So x would equal plus or minus the square root of y. In our case, because we're to the right of the y-axis, we'll just use the positive one. So it's going to be square root of y minus 0, or just square root of y. That's going to be my R2. Why don't you take a turn and solve for R1? What's R1 going to be? If you're watching this later, you can pause the video, try and figure it out yourself. But see if you can't figure out the expression I'm going to put in here for R1. What you got? Anyone? Yeah. If you solve for x, you get 1 over 4 times y, or y over 4. So 1/4 y minus 0, or just 1/4 y. So good. Those expressions are going to get substituted in. And I'm going to kind of move on to another sheet of paper because I don't want to cram everything in here. So this is example E still, continue. Volume of one washer is going to be V equals pi times R2 squared minus R1 squared times dy. R2 is going to be square root of y squared minus y over 4 squared again times dy. And it's not a bad idea to simplify this. That's going to be pi times y minus y squared over 16 dy. Whew. Deep breath. Deep breath. What are our limits of integration going to be? This is going to be our integrand. Integrand, I'll take the pi out front. Y minus y squared over 16 dy. Well, what should be our limits of integration? 0 to 4 would be in terms of the x-axis. we took a dy slice. We want to know where y can vary between. So the lowest that this could be and still be in this shaded region would be y equals 0. What's the top? 16. If you didn't have a nice graph, how would you solve for where that y limit exists? Yeah, set them equal to each other. So yeah, set them equal to each other. You'll get x equals 0 and x equals 4, but then you're going to plug in and find what y equals, and y is going to equal 16. So 0 to 16. Your choice. Do you want to solve this out exactly, or do you want to do it after an int? All right, I heard that exactly. Good. Good to hear. I'm glad you want to think a little bit. Nice to hear. So I need an antiderivative here. Isaiah, what would be an antiderivative for this one?
Y over 2.
All right, y over 2.
Over 2
You might want to regard that as 1/16 times y cubed.
Do you mean y squared?
Y squared, sorry, y squared. So 1/16. What's going to be the antiderivative of this part?
It's going to take me a minute to figure it out.
It's all right. It's kind of what you did to this one. Add 1 to the exponent, divide by that same exponent. So if you add 1 here and divide by that same exponent, what would that give us?
So 16 over 3 or?
Y cubed over 3?
Yeah.
All right, good, thank you. So it's going to be pi times 0 to 16. I'm going to write that as 1/2 y squared minus 1 over 48 y cubed. Oops, sorry, I didn't realize I was kind of off screen there. So it's going to be pi times, let's see, 1/2 of 16 squared, so 1/2 of 256 minus 1 over 48 times 16 cubed. Boy, that's 4,096. Someone help me out on that. Is that right?
Yeah.
Whew, man, all right. Good job, professor guy. So pi 1 times 256 minus 1 over 48 times 4,096. Let me ask you a question. I can't exactly tell right now, but I'm curious. Could I end up with a negative number here? Should I end up with a negative number here? No, because you're talking about a volume. Volume should be a positive number, so let's see here. So it's going to be 128. I don't know what the rest of that's going to be. Clear. So 128 minus 4,096 divided by 48. And let's hit the answer to fraction key. So 128 pi over 3. Whew. Good one. Good one. A lot of work to get that one. The big thing that you need to see, though, is that because this region wasn't flush, wasn't completely uptight against your axis of rotation, that's why we got that little gap there that resulted in this being a washer method as opposed to a disk method. So if there's a gap, probably gonna end up with something like this, a washer instead of a disk.
What was that 0 portion where you subtracted 0 from the radius? What does that represent graphically?
So graphically, what you're doing is you're finding the distance along the x direction. And when you do that, it's always the left-hand endpoint minus the right-hand endpoint. So if I wanted to find the distance between these two, it'd be 3 minus 1. In our case, we had some point, call it x, minus 0. Now, the only reason I do that is because you're not always gonna have an axis of rotation that's gonna be either the X or Y axis. So I'm just getting you in the habit of subtracting top minus bottom or right minus left. It's when this is a number that's different than 0 that you're gonna have to pay more attention. Yeah, no, I appreciate the question. All right, let's take a little bit of a break.